But for quasi-Hopf algebra, if you take the dual, it is not quasi-Hopf algebra anymore. So we always call its dual a modular algebra. So in my talk, a quasi-quantum sometimes means a quasi-Hopf algebra, sometimes means a modular algebra. So that's the reason. My talk is divided 3 parts. The first part, I want to compare the Hopf algebra and quasi-Hopf algebra. From this, maybe we can accept the concept of quasi-Hopf algebra more easily. Okay. Then I want to recall why we need the quasi. This is a quite complicated concept. Why we need it, and from my point of view, I collected some short history about its development. Then at last, I want to introduce some of our works and put some questions for our future research or for your test maybe. So at first, I want to recall the Hopf algebra and quasi-Hopf algebra. We need to establish its concept explain its concept at first. So in my talk, I use a K or such kind of a K means algebraic closed field with characteristic 0. So in my talk, always algebraic closed field with characteristic 0. Okay. Everybody know associative K algebra is just defined to be a triple, where A is a K space, linear space, and M, sometimes we call it multiplication from tensor, so it is a linear, okay? From A tensor A to A, and mu just means a unit. From K to A is a map, such that the following diagrams are commutative. We know the first diagram means it is associative. The second diagram means it has a unit. So that is a associative K algebra definition. In such a way, it is easy to get a dual concept. The dual concept is called co-associative co-algebra. Co-associative co-algebra. Okay, it's defined to be a triple. Just reverse all the directions in the diagrams, you can get the concept of co-algebra. So at first, C just a linear space, and the delta, you see direction is inverse. We can inverse the direction. From C to C tensor C epsilon, from C to K, and such the following diagrams. In the formal way, maybe easily to generalize the concept, but if you study the Hopf at first, I still recommend you to find more examples. Otherwise, this formal language, I think, is not useful for our understanding of our understanding some algebra structures. So if you want to know more about the co-algebra, I strongly recommend you take some examples, especially you take some quite simple associative algebra. Then you take the linear dual, you can find it will be a co-associative co-algebra. And I recommend you write out what's the meaning of these diagrams. Maybe you can get a well understand. Okay. Next, I want to combine these two concepts together. So a bi-algebra is both algebra and a co-algebra. And these two algebra structures are compatible. What's the meaning compatible means the co-algebra maps are algebra morphism. So we need the co-algebra maps are algebra morphism. Equivalently, you can ask the algebra maps are co-algebra morphism. Okay, that's the equivalent definition. That's totally the same. So this definition of bi-algebra. So what's the meaning of Hopf algebra? Hopf algebra just a bi-algebra plus another linear map. We call it antipode. Why we call it antipode? So, okay, the definition of antipode is just the following, just this. Okay, just this equation. So from S1 prime H double prime equal to this. Why we call antipode? If you want to understand it, I recommend you to find the prototype example of Hopf algebra. The original example of Hopf algebra come from the sphere, okay? Come from a three-dimensional sphere. You can find the antipode just means we take the antipode point. So that's the reason why we call it antipode. The one typical property of Hopf algebra is an antipode. If it exists, it must be unique. So in this reason, we can sometimes we say that antipode is a property of bioalgebra, not say it's additional structure, because more or less it's just unique. Okay. We will find in quasi-Hopf algebra case, this uniqueness, we don't have the uniqueness. This causes many troubles to us. So next, we can recall the definition of quasi-Hopf algebra. Quite similarly to the Hopf algebra. A quasi-Hopf algebra is just mean a quasi-bioalgebra, okay, quasi-bioalgebra, and plus antipode, and plus some compatible conditions. So the key point is we need to explain what's the meaning of a quasi-bioalgebra. So a quasi-bioalgebra is similar to the algebra, but more complicated. It's become sextuple, okay, where H, mu, M, and mu is algebra. So at least a quasi-bioalgebra at first is the associative algebra. Then it's with two algebra maps, delta and epsilon. So it's quite similar to bioalgebra. But the key point is that it has no co-associative co-algebra structure. So that's meaning. What's the meaning? It has no co-associative property. So the meaning of the co-associative means that there's no such phi. You see, co-associative means there's no phi. But for quasi-bioalgebra, the co-associativity is replaced by conjugation by a invertible element. Okay, after a conjugation of this invertible element, it is co-associative. Associativity is available. We have, but this phi, we have additional requirement about this phi. Phi, we must ask it satisfy a Pythagorean relation. Okay, Pythagorean relation. A last relation is a normalized relation. Maybe it's not so crucial. Okay. Maybe you can ask why we can find such a very complicated concept associator. So we will tell you the history why we can when we find such a element associator. Anyway, at this moment we need to accept this concept. Okay, that's the meaning. The co-associativity is not valid now, but it's valid up to a conjugation of an element phi. This phi is called associator. So associator is a very key point in our talk. So now if we denote associator by this in this notation, okay, the antipode, we saw antipode define also a algebra antimorphism is called antipode, and the other two elements and satisfy such following compatible conditions. Maybe we'll find that this compatible condition is much more complicated than Hopf algebra case. So I have to say the Dreamfield is great. Okay, this Dreamfield invent this definition. We will recall why he finds this definition. Okay. For the quasi-Hopf algebra, we have very important two concepts. Two concepts is very important for the quasi-Hopf algebra. At first, we want to introduce the first concept. We call it the gauge transformation. the gauge transformation also introduced by the Drinfeld. So what's the meaning of the gauge transformation? So an invertible element belongs to the H tensor H is called a gauge transformation. If it is satisfying this condition is not strong. Actually, it's very loosely, very loose condition, I think. So to find such element is very easy. So you find a gauge transformation is very easy. You can find anywhere, anywhere. So why we need this concept, gauge transformation? The reason is if you're given a gauge transformation of H, one can construct another quasi-Hopf algebra, Hj. What's the meaning of Hj? Hj as an algebra just totally the same as H. So the algebra structure does not change. Of course, the linear space also not change. The only change is the coproduct. Of course, if you change your coproduct, you can find associated will be changed accordingly. Anyway, you can change your associated accordingly, and other elements you can also get another quasi-bialgebra or a new quasi-Hopf algebra. But only I need to remind you, the difference is just the coproduct. The coproduct is changed up to a conjugation by the J. So from the gauge transformation, we get another concept. So we call the two quasi-Hopf algebra HK are called gauge equivalent or twist equivalent, denoted by H, sim, K. If there is a gauge transformation J of H such that K isomorphic to the Hj as a quasi-Hopf algebra. So this concept is very important for the quasi-Hopf algebra. Actually, Drinfeld says that. So if you read the Drinfeld paper, Drinfeld says that the gauge transformation can simplify the study of quasi-Hopf algebra. And so there's a lose. This poses a very fundamental question to us. So if you take the gauge transformation, you get a variety of quasi-Hopf algebras. In this variety of quasi-Hopf algebra, which one is simple? Which one is simplest? That's meaning you can find a canonical model in this variety of quasi-Hopf algebra. This is a very big question for us. But up to our acknowledgement, I don't know any advanced, any general or any nice conclusions in this direction. Actually, we know very little about the quasi-Hopf algebra. So there's another reason why we need the gauge equivalent. So there's a typical result in the Hopf algebra or quasi-Hopf algebra. You can prove that two finite-dimensional quasi-Hopf algebra are gauge equivalent if and only if their representation categories as tensor categories are tensor equivalent. As a tensor, so that's the equivalent. So this tells us to study the gauge equivalent class, it's equivalent to study the tensor categories up to the tensor equivalent. Okay, the equivalent. That's also the reason. So before we recall the second fundamental concept in quasi-Hopf algebra, we need to tell you the difficulty in and history of the quasi-Hopf algebra. So comparing with Hopf algebra, for me at least, although Drinfeld sometimes says that research quasi-Hopf algebras sometimes become easier than Hopf algebra, but maybe I'm too stupid. I don't understand. I still don't know how to deal with the quasi-Hopf easily way, except you use the tensor category way. So comparing with Hopf algebra, there are three uncertainties for us about quasi-Hopf algebra. Why? At least we can say that the co-multiplication is not so unique because, as I told you, classification of the quasi-Hopf algebra usually classified up to gauge equivalent. You know, Getty equivalent. In the definition of the Getty equivalent, you can find we always change the coproduct up to a conjugation of the invertible element. So that's the reason the co-multiplication is not so unique. If we fix the if you fix the co-multiplication, then you can find the antipode is still not unique. And we have many antipodes. If even you fix the co-multiplication, you find many. Of course, you can find antipode is orbit. Okay, up to a group. The group action. Okay, this group is very large, very large. So the antipode is not unique. This also causes many difficulties. And maybe we know some words from Dreamfield himself. Maybe Dreamfield sometimes told us that this definition, when he gives definition of quasi-Hopf algebra, he maybe not consider it very carefully. He gave the definition, but maybe he don't think the definition is very satisfied. But at the moment, we accept his definition, and we faced many difficulties. Of course, even you fix the co-multiplication and you fix the antipode, the element alpha beta are also not unique. Alpha beta also can be changed. Even today, we still don't know alpha beta is invertible or not. Alpha beta are element in H. All known examples showed us they are invertible elements. But is it always true? We don't know. So I have to say, we know very little about quasi-Hopf algebra. Such questions are very fundamental for me, but we don't know the answer. Maybe we are very stupid. Okay, very stupid. Before we going to say we are stupid, but I want to give some evidence to convince us we still know something about Hopf algebra, quasi-Hopf algebra. So what are we knowing? Okay. What are we knowing? Before we're knowing, we need to tell you why we need a quasi. It's so complicated concept. So I think the quasi-Hopf was invented by, I believe, the history is the Dreamfield invented this concept. The motivation of Dreamfield find the connection of the quasi-quantum groups or quasi-Hopf between the quasi-Hopf and the Konishnik, the Molotov-Chekhov system of equations. This is the linear equations or linear partial equations system of linear partial equations. So, why he consider what's the relation between this system and the quasi-quantum quasi-Hopf algebras? The motivation of the Dreamfield is want to give a direct understanding of Cornell theorem, one of Cornell theorems. So what's the Cornell theorem? Cornell theorem says that if you consider this linear equation, you can construct a flat connection over of a trivial bundle over the underlying space. The underlying space, you can consider the underlying space as an endpoint configuration space. You can find the endpoint configuration space, the fundamental group of this space is just a purebred group. Use some technical way, you can construct a bread group, not only a purebred group. So you consider the monodromy representation of this flat connection, you can get a representation of this bread group. So what's the meaning of the Cornell theorem? Cornell theorem says that this monodromy representation of the bread group is equivalent, please remember, is equivalent to representation given by a universal R matrix. Which universal R matrix? Also, the R matrix is constructed from this simple, semi-simple Lie algebra, this quantum group part you can construct. So, you know, Dream field is a must of must of universal matrix, and is also a must of quantum group. So dream field, I think dream field want to concede. He want to give a direct understanding of quantum theorem. He thinks this question will provide us a universal armature or similar to a universal armature. This such kind of elements should be exist. So dream field to construct, and of course dream field realize the asymptotic behavior of the equation. The braiding you can write very easily, but from one asymptotic behavior to another asymptotic behavior, there's a difference. Because this difference, dream field finds this difference will create a new element. This element is called dream field associator. So dream field point is that can the equation give rise directly to a quasi-triangular quasi-Hopf algebra? We'll give it directly, okay? He find the associator. The associator just the difference between two locally asymptotic behavior. This is called dream field associator. So dream field find this associator will force that the representing category of this algebra structure will form a tensor category. So he need proof that the phi must satisfy the pentagon, the hexagon, and some other axioms. So dream field proved it. So that's meaning why we need quasi. The first reason, dream field think we need quasi. That's the reason we need quasi. Dream field is genius. He find the dream field associator. This is a very complicated element at the moment. Very complicated. Of course, we can list some other reasons to say that we need the concept of quasi-Hopf algebra. For example, Majid proves that given a TFT, okay, maybe the TFT is not a standard concept to you. For me, okay, for my talk, TFT just means a tensor category together with a quasi-fiber functor. Just the definition. Okay, this is not a standard definition. It's not a standard. Majid proves that if you give a tensor category together with a quasi-fiber functor, we can get a quasi-Hopf algebra. Please remember, not a Hopf algebra in general. So we'll get a quasi-Hopf algebra in general to make the representation category of H is tensor equivalent to this TFT, to this tensor category. So this means quasi-quantum groups sometimes are more natural than quantum groups or more natural than Hopf algebra in dealing with TFTs. That's the reason. Okay, one reason. Also, another reason is recently, especially in the years after 2000, the interest about the structure of tensor categories, we feel more and more interested. So we also want to classify fusion categories. We also want to classify the finite tensor categories sometimes, and also some other kinds of tensor categories. So recently interest in researching and classifying finite tensor categories, we also need some knowledge about quasi-Hopf algebra. That's very natural, very, very natural. Because a quasi-Hopf algebra, you can prove quasi-Hopf algebra exactly provides the tensor categories with every object have a Frobenius dimension are integers. So quasi-Hopf algebra give our test or some examples to understanding general tensor categories. So that's the reason. Also, another point is it provides a bridge, or at least it provides a bridge from Hopf algebra to tensor categories. You know, Hopf algebra more or less is quite more special than quasi-Hopf algebra. So quasi-Hopf algebra become a bridge between Hopf algebra and general tensor category. For example, I just take an example to convince you this is also useful. For example, for Frobenius indicator, we know Frobenius indicator is introduced, of course, introduced by Frobenius. Frobenius, there's, oh, sorry, there's a C missing. Okay, FCHU. For initial indicator, we know Frobenius and you want to consider one irreducible complex representation when such a representation is a real representation. You see, you can find that the character is real is not enough to make this representation is really a real representation. So he needs another invariant. This invariant is called Frobenius indicator. From Hopf algebra point of view, you can find the Frobenius indicator can be defined through integrals. Okay, so that's the reason why Nanjing and Montgomery, Susan Montgomery, in 2000, they generalized the concept of Frobenius indicator from the group algebra to Hopf algebra, to semi-simple Hopf algebra. Then in 2005, the Frobenius indicator theory was established for quasi-Hopf algebra by Geoff Mason and Richard Ng. In the last week, he gave a very nice talk. In 2005, then maybe they use it, maybe they're not. From reference, they use of course, use some computation result in quasi-Hopf algebra case, and established the general Frobenius indicator series for pivotal categories. Pivotal, not only fusion, you can remove the fusion restriction. For pivotal finite tensor categories, you always can define the Frobenius indicator. So you see, it's established by Richard Ng and Peter Schellenberg in 2007. Okay, that's just one example. You can find other example. You tell us that quasi-Hopf really provide a bridge from Hopf to tensor. I'll say, okay, now we from this point you can think maybe quasi-Hopf is sometimes it should be useful. Okay, should be useful. So this provide our motivation or our we can put many sometime to research quasi-Hopf algebra. So research quasi-Hopf is not does not waste our life. Okay, in order to introduce the development of quasi-Hopf, we want to introduce the second very crucial concept in the study of quasi-Hopf algebra. This concept is called genuine. So we call quasi-Hopf algebra is called genuine if it is not get equivalent to a Hopf algebra. It's a very natural concept because if it get equivalent to a Hopf algebra, that's the reason we can use it. We can reduce the study of quasi-Hopf algebra to Hopf algebra. So the problem become a problem about Hopf algebra. So this concept is very necessary and very natural. So there's a more natural question is, do we have a genuine quasi-Hopf algebra? Of course, the answer should be yes. If the answer is negative, that means we needn't waste our time to research quasi-Hopf algebra. Of course, the answer should be yes, but the situation is not so optimistic. Why? I give you some example to explain this phenomenon. At first, for Drinfeld, okay, Drinfeld proves that Conal theorem. He give another way to prove the Conal theorem. The key point is he proves that the quasi-triangular quasi-Hopf algebra he construct exactly equivalent, get equivalent to the usual quantum group. In this way, he realized the Conal theorem. The Conal theorem says that the Bragg group representation is constructed from a universal R matrix, where the universal R matrix is here. So, but from the study of the quasi-Hopf algebra, we find that the quasi-quantum group constructed by Drinfeld is not genuine. Yes, because it is equivalent to a Euro quantum group, so it's not genuine. So there's no genuine quasi-quantum group associated to simple algebra or semi-simple algebra. No direct way. Okay, direct way. Actually, I have to say, we know very, very little about the infinite dimensional quasi-Hopf algebra. Very little, very, very little. From my acknowledgement, we even, except you use some artificial way, you can construct some genuine infinite dimensional quasi-Hopf algebra. There's no natural examples of infinite dimensional quasi-Hopf algebra which are genuine. From my acknowledgement. But in the 1990, there are three physical mathematicians. Okay, they construct a quasi-triangular semi-simple quasi-Hopf algebra d omega g. What's the meaning d omega g? Actually, it's just a quasi-Hopf analog of the usual Drinfeld double of group dg. Maybe you knew dg, the Drinfeld double of group algebra. We know much about Drinfeld double of group algebra, but we know very little means what's the meaning of a quasi-Drinfeld double of the group. Okay, these three mathematicians construct such quasi-Hopf algebra. Maybe you can ask why they can find this. Okay, they study the VOAs. The VOAs, they find it. Yeah, the way. The natural question is, are these quasi-Hopf are genuine? I would say some of them yes, some are no. So in the next 15, but I have to say in the next around 15 years, maybe d omega g, maybe the only known examples of genuine quasi-Hopf algebra. This is a class of quasi-Hopf algebra, so it provides some genuine quasi-Hopf algebras, but some of them are not. I have to say, to determine whether quasi-Hopf is genuine or not is not an easy task. Actually, if you read the Cherry Presley's book, A Guide to Quasi-Quantum Groups, they say that d omega g is genuine if omega is not a trivial spherical cycle. Trivial means it is not. Trivial means it is a cobinary. But I have to say this is not. This statement is not true. Actually, that means you can find easily, maybe not easily. You can find some non-trivial spherical cycle, but d omega g is still not genuine. Okay, you can find it. This also tells us that it is not easy to determine whether a quasi-quantum group are genuine or not. Okay, even in the textbook we can make some mistakes. I have to say, in the next 15 years, what we done? In the next 15 years, we maybe we not stop, but no essential development. But we do some work. So, for example, the integral theory, the Drinfeld double theory was generalized to quasi-Hopf. Maybe you can think this is quite straightforward, but not so straightforward. For Drinfeld double, I'll take example to say that the Drinfeld double of quasi-Hopf algebra may be not trivial. For example, if you recall the definition of Drinfeld double or Hopf algebra, we can find you need to consider the dual of this quasi-Hopf algebra. But I have to say, the dual of quasi-Hopf algebra is not associative anymore. Okay, it's not associative. The original quasi-Hopf algebra is associative, but the coalgebra is not associative. So it's dual, the coalgebra is associative, but the algebra is not associative. If you're combining these two algebras together, what will I get? What we will get? It's associative or not associative. So that's the contribution of Majid. Majid proves that. Although his proof have some gaps in his proofs, but he gave intuition. His intuition is correct. He told us the Drinfeld double quasi-Hopf algebra is still a quasi-Hopf algebra. It means as algebra, it is still associative. Okay, we fix this gap by Scharenberg at last. and others, of course, not only Schoenberg. So that's the reason why sometimes we call the dual of quasi-Hopf, we call it modular algebra. Okay, modular gives some contribution. If you say in this direction, you give a contribution. It gives a contribution. The new development should built by Dirac and Eddington. From 2004 to 2006, Eddington and Dirac published a series of papers, maybe more than 3 papers, but I just want to describe its final result. Their final result can be stated as follows. So they classify, please remember, not only construct some genuine quasi-Hopf, they classify, not only construction. He gives some classification. So that's an essential contribution to this direction. So they classify all elementary quasi-Hopf. What's the meaning elementary? Elementary means their simple modules are one-dimensional. All the simple modules are one-dimensional, means elementary. Okay, they're all elementary quasi-Hopf algebra satisfy H modulo is Jacobson radical isomorphic to the KZP. ZP means cyclic group of order P. P is a prime. Okay, that proves this result. And even Giono generalized the Eddington of Dirac is this result further. And finally, he classified all basically means element the same. Quasi-Hopf algebra over cyclic group. Over cyclic group means H modulo G is a cyclic group. So it's comparing with Eddington's result, Eddington Dirac's result. He generalized the P to the general N. Okay. I have to say, the Evangelion essentially provide very little new examples. Okay, essentially no new examples actually. Just say all the results or the techniques developed by the Dirac and Eddington Dirac can be generalized to the general N case. And also he applied the techniques from Snyder, Andrew Snyder, and Snyder, they clarified results about the general point-Hopf algebra techniques. He provided such techniques. Okay, in this case. Next, we do some work in this direction. At first, when we consider this question, we first want to classify the quasi-quantum groups according their representation type. In my PhD thesis, I research classify the Hopf algebra according to the representation type. So we want to generalize such idea to quasi-Hopf algebra, and we made some success. For example, for representation finite pointed modular algebra, we can classify it. And also for term type, we also can classify it. But it's a pity, I have to say, it's a pity that in these 2 papers, we actually don't find essential new examples of quasi-Hopf algebra. Generally, it's very generally. Of course, many of them are generally. And but it's not new. Actually, our examples more or less recovered by previous works by Eddington, Dirac, and Angel. Okay, but the new development should be the next state. At last, we know how to construct the quasi-Hopf analog of the Frobenius kernels. That's really an improvement in the direction. Okay, direction. So in 2017, we construct many new genuine quasi-Hopf algebra. There's many classes. That just mean if you give a simple algebras, we can construct. And then use such example examples and the techniques we developed, we can classify more general quasi-Hopf algebra or modular now. So in the last 2 years, we classify all the graded, connected, pointed, modular, or diagonal type. Okay. And also for non-diagonal type, we also the people also get some development. So you can see this paper for diagonal, but the method is similar to above. Method is above. So next, we want to introduce our 2 works about this direction. The first work is construction of quasi-Frobenius kernels. And when I consider the question about the quasi-Hopf algebras, I feel curious. Why is there no people to consider Frobenius kernels for quasi-Hopf algebra? I feel very curious. When I consider very carefully, I find that this is not. I don't feel curious now. The reason is we need to recall who find the Frobenius kernel. This is Lustig, George Lustig. How George Lustig finds this example? Actually, Lustig finds that for if Q is a primitive root of a unity, and you can consider, of course, you can consider integral form, Z form, and anyway, Lustig finds that in this form there exists a sub-Hopf algebra, Hopf subalgebra. This is a finite-dimensional Hopf algebra. It plays very similar role to Frobenius kernel, okay, in the modular algebra group, quite similar. So that's the reason at last we call this finite-dimensional Hopf algebras the Frobenius kernel. And you find that Lustig find the example, he need a bigger quantum group. In this big quantum group, he finds sub-Hopf algebras. So that if you apply the same idea to find the quasi-Frobenius kernel, you also need to find a quasi-quantum group, big quantum group, and find a small. But as I told you, we have no such quasi-analog for quantum group, because Stringfield himself proved that. He constructs the quasi-quantum group is equivalent to the usual quantum group. I think more or less is the reason why we spend so much time to find the quasi-Frobenius kernel. And the lucky point for me, we still have another way to construct the Frobenius kernel. This is the Hopf algebra way. So that is you can construct a Drinfeld double and modulate something, you can get the Frobenius kernel. Okay. So my point of view is this way survive in quasi-Hopf case? That's the way I consider. I want to consider this question. And so we have some good news. So this means this way may be succeed, because in 2006, Jelinek already give a quasi version of a tough algebra. You know, if you know, for the in the Frobenius kernel, the smallest or simplest is UQSL2, small UQSL2. You can find the small UQSL2 is the quotient of a Drinfeld double of tough algebra. So if you want to realize this way, you need to find the quasi-Hopf analog of tough algebra at first. Okay, but when I check the reference, we find that Jelinek already finished this work. He gives a quasi-Hopf analog of the quasi-Hopf algebra. We don't want to the detail of this example. Anyway, you can find its co-multiplication and antipode become more complicated than Hopf algebra case. Okay. Maybe there's another lucky point for me. Before I read further references, I want to compute this Drinfeld double directly. In fact, any regularity proves the following example. If I know the example, I will feel very disappointed. Okay. Any given hierarchy proves that if n is even, you know, top algebra will depend on the natural number of n. If you just depend on the natural number n. And any given hierarchy proves that if n is odd element, is odd, he proved that even you compute the trivial double, this trivial double just the Euro UQSL2 also get equivalent to this. The lucky point for me, before I know this right, I start my computation. Maybe in the middle of my computation, I find this result, and when I find this result, I feel very, very disappointed. I feel maybe I will fail. I feel that I will fail at last, because if n is odd, you cannot create new quasi-Hopf algebra. Especially, you cannot create any general quasi-Hopf algebra. This result told us. But the lucky point is I don't give up my computation. I continue to the computation. At last, I write up the generator and the relations of this double. Okay, I construct a new quasi-Hopf algebra through the following generator and the relations. Okay, and I prove this trivial double just this quasi-Hopf algebra I constructed just the usual trivial double of the AQSL2. And the lucky point is I prove that if n is even, this quasi-column is genuine. So I should thank Professor N.G. Richard providing me some idea to prove this result. But at last, we get this result. This gives me a confident, So this make me feel that. So the first feel is the quasi-Frobenius kernel seems not a generalization of Frobenius kernel, but maybe more parallel to the Frobenius kernel. Okay, because n is odd is a Euro, n is even, you can get a new. And that's the reason it seems the parallel theory, not just a generalization. Okay, not a generalization. And also you can find this dream field has a much more nice representation theory than the Euro dream field. Okay, more nice, at least from my point of view, more nice. I don't want to recall the representation theory now. And the same idea you can generalize to the general simple algebra. This is not difficult, not difficult. As long as you want to spend some time to computation, you can fix. So I can recall, I can go very fast to the story of the general, a story of a general simple algebra. So the method used to construct UQSL2, QUQSL2 can be generalized to other simple algebras. And because the anti hierarchy also constructs the quasi-Hopf analog of the half part of the quasi-quantum groups, that's the AQG. And we compute is dream field double and define the following quasi-Hopf algebra. So you maybe this relation is not so complicated, but if I write out the co-multiplication and antipode, you will find it's become much more complicated than our Hopf algebra case. You see, but if you don't know the computation of UQSL2, I think it's almost impossible to get such complicated formula. Anyway, we prove that the double is just the quasi-Hopf we construct. And it's a pity. Even I construct such a quasi-Hopf, I don't know whether it is genuine or not. Complete list, I don't know the complete list. Sometimes I know. At least I read a theorem here. If G is a type A, And for type A, if m plus 1 divides n, then this Hopf is genuine. And also for type A, if m is odd and 4 plus divides n, then this one is all genuine. For type B, we also find some sufficient condition to make it genuine. And C and D and E7 also sufficient condition. But for E6, we also have a sufficient condition. But maybe you can ask me why there's no E8, F2, and F4 and G2. For these three cases, I don't know. Actually, I don't know. But I can give you a conjecture. At least I don't know how to prove this conjecture. For type E, because it's very complicated, very complicated. For type E8, I think for E8, this one cannot provide genuine case. So it always twist equivalent for Hopf algebra. For type F4, and I guess a sufficient condition. And for type G2, okay, this all give a sufficient condition. So I pose a question here, but this question may be not so easy. So can you give a complete list of general quasi-Hopf loose kernels? Even I construct them, we construct them by generator and relations. Reconstruct them. So I don't know the answer at this moment. Next, for more, this idea can be generalized further. Okay, generalized further to consider other Cartan type. You know, in the classification of pointed Hopf algebra, we can generalize our Fulmin's kernel theory to the Cartan type Nichols algebra. Okay, so the Cartan type also generalized by can be considered by some experts here. For the second work, I want to recall our class result about graded pointed modular algebra of diagonal type. So I need to recall that the modular algebra is just a dual quasi-Hopf algebra. So the classification is totally the same as the classification of quasi-Hopf algebra. I just take an example to explain our idea, why we can succeed. So take which example? The example, I just consider the rank 2 case. Rank 2. Rank 2 means because it's graded. So the graded 0 means M1 is over M0 is a rank 2 free module. This rank is this meaning. Rank 2 free module. By our assumption, you can prove that M0 must be a group algebra together with 3 cocycle weight. So in order to classify this kind of modular algebra, maybe M0 part you need very clear. You need to give a structure of M0 part. So this lemma told us the M0, this G should be Zm times Zn, this form. Okay, just this form. You can use the condition. So the kind of group is very easy. So next task you need give all the 3 cocycles. So in next computation, you can find all the 3 cocycles can be given a unified formula to give the 3 cocycles. I need to point out that we know the 3 cohomologies, but we don't know much about 3 cocycles. Okay. For our point of view, we don't need the 3 cohomologies. We need a unified formula for the 3 cocycles. So we need put some time to give a unified formula for 3 cocycles. So anyway, in 0 part, M0 part is clear to now. Yes, clear now. And a key point is we can construct a big group, bigger than the original G. We can take a big group and form a surjection of morphism. We take the surjection of morphism. If you take this surjection, you can pull back the 3 cocycle from this group to this group. Okay. Okay. The point is, if you take this this black group is good enough, you can find that the pullback of this cycle is become a coboundary. So we give a way to resolve this cycle. So the very key point. This means the original cycle in a small group, you can find a big group. And the big group, in this big group, the cycle become trivial. It become a coboundary. This means the cycle can be resolved. Okay. The point is, this means it can become Hopf algebra at last. Next, we should remove our concentration on the M1 part. So to consider this part, we need divide M to two parts. One is M0, another part is R. R, if you familiar with theory of Hopf algebra, R sometimes is called Nichols algebra. So next part, we need to consider the Nichols algebra part R. Also, another point is we prove that R is not only a Hopf algebra in the original this Yet-Trinfeld module, in the category of Yet-Trinfeld module, but also in this bigger group, Yet-Trinfeld module, the category of Yet-Trinfeld modules. Okay. Please remember, in this big group, this three cycle can be resolved. They become boundary. What's meaning? If it become boundary, this means this quasi-Hopf algebra is actually a Hopf algebra because it can be get equivalent to a Hopf algebra because associated disappear. Therefore, we can form a big modular algebra, and this bigger modular algebra should be twist equivalent or get equivalent to a point Hopf algebra. So what I say is just this line. So you take the original modular algebra, you can construct a bigger modular algebra, and you find this bigger modular just ordinary point Hopf algebra. The key point another key point to classify modular is to find a return ticket. So it means which kind of Hopf algebra can provide coming from which kind of Hopf algebra coming from the original modular algebra. You need to classify this Hopf algebra. So the questions remove to the classifying of the Hopf algebra. So at last we find this such Hopf algebra just only need to satisfy a congruence equation, linear congruence equation. That's enough. So this linear congruence equation, of course, anyway it's linear, so it is possible for us to resolve it. You can find in this equation n, m, alpha 1, alpha 2, beta 1, beta 2 are unknown. All of them are unknown. Unknown elements are a, b, and d. So for a, b, d, only 3 unknown, but we have 4 equations. So it means sometimes we have no solutions. But if we have the solutions, more or less it to be unique. This is true. If we had a solution, it had most one solution. Okay, this is we call it equation. The equation 2. Please remember this notation 2. Okay, equation 2. This equation. Now we just want to explain the meaning of knowing characters. So you needn't care about it. And about the congruence equation can be simplified to the following one equation 3. Okay, so the equations 2 has at most one solution, and it has a solution if and only if this equation is satisfied. So if you find the original quasi-Hopf algebra, this equation is very easy to find it's true or not. Okay, no. So anyway, if you take the original Hopf algebra, you can take the converse procedure. Yes. And if if 2 or the 3 equation and third equation is soluble, and you can get the original modular algebra. This way give our way to classify the original modular algebra. So next, just some technical technical terminologies for terminologies technical. So we call it rank 2 Nichols algebra is set to magic type. Magic type means it can construct the original magic algebra. So how to construct? We give a way. If you take the magic type BV and through this way you can construct the original magic algebra. Okay, magic algebra. So this MVG is essential. All of rank 2 magic algebra. So we can list our last theorem. Last theorem we divide 2 parts. First one, MVG is a finite dimensional kinetic graded pointed magic algebra rank 2. Then we find we say that all finite dimensional, if it is a finite dimensional connected graded correctly graded point modular algebra rank 2, then it must isomorphic to some MVG. Okay, this give a complete classification of such kind of modular algebra. Of course, we give some many restriction here. For example, connected is not essential. It's a technical point. If you remove it, still you can build a similar result. But theoretical gradient, this is essentially. Gradient is very essentially. Okay. So this leaves us a very, very big problem. How to lift. How to lift our classification to ungraded case. For Hopf algebra, we have a procedure for lifting procedure. In many cases, this lifting procedure can apply. But for quasi-Hopf algebra, a big, very big problem for us, or big difficulty for us is how to lift the dream field associator. How to lift it? In our graded case, this associator is reduced just to a 3 cycle. But for general dream field associator, it looks like iterated. It looks like iterated 3 cycle, 3 cycle over 3 cycle over 3 cycle. Iterated very goes step to infinity. We don't know how to control it. So at the moment, we maybe find an idea. Maybe we try an idea to solve such this problem. Anyway, I have to say, at the moment, we don't know how to lift dream field associator. So this question should relate to the following questions: how to compute the cohomologies of quasi-Hopf algebra? Actually, not only for cohomology, original cohomology is not easy. Okay, even for group, even for some nice variety or nice manifold, you still don't know how to. Of course, for general algebra and general quasi-Hopf, there's no answer, of course. But for some special, especially for some special, would you find some special? Or some special quasi-Hopf algebra, and you find the way to compute the 3 cohomology. We don't know. We don't need the general cohomology. We just need to know the 3 cohomology. That's enough for us. These 2 questions should be related to each other. And I want to pose other question to you. So, for example, when the elements alpha beta are units, maybe if you can prove alpha beta are general units, that's a very good work. But in general, you don't know how to prove it. Maybe in some natural conditions you can prove it is also true. Is also not very bad for me, I think. Also, you need to the understanding what's the meaning of alpha beta are units. What is use other way to understand it? Okay, I put such question for you. That's all the talk. Thank you very much. That's all. Thank you very much.
We thank Professor Liu for the great talk. Are there any questions? You can ask in Chinese if you want. Do you have any questions? I have one. Can we go back to the
okay, slide?
Yeah. the Frobenius-Lustig kernel part
Yeah.
that you talk about. The Q, U, QG.
Yeah.
Okay.
Okay. QUG.
The result that you the theorem that you have for the generally
General
algebra.
G.
Yeah. General G.
Okay. Here.
Okay. Yeah. So let me can we look at the theorem? The genuine
Here.
part. Okay. Yeah.
This
So the
one.
m+1. Yeah. Let me
Yeah.
see. This odd and then this. Okay. Oh, okay. It seems that the m+1 for type AM and let's see the 2 and 4 they're all and 3 for E6. These numbers are the order of the center of the algebra. That is the root lattice, the weight lattice mod the root lattice. So for type AM, the weight lattice mod the root lattice is Z mod m+1. And for type BM, the center is Z2. So you see 2 here. And for C and type CD, oh, not E7, but for type C and D, the center are Z2 and Z2 and Z4. Yeah, and for E6, the center is C3. So maybe there's something. It has something to do. The genuine has something
Relation.
to do with
Okay.
with the center. That's my comment that I want to make. Yeah. And also you have this alpha for this quasi-Hopf algebras. Are these units? They look like a big sum over a product, right? The alpha. Yeah. Is alpha a unit for this? Yeah.
Yeah. Here alpha is unit, of course. Alpha.
Oh, okay.
Yeah. This is unit. Beta is
this
one.
is unit.
A unit.
Okay.
Yes.
Okay.
It's unit.
Okay.
Although it's look very complete, but it's unit.
Okay. Yeah. I'm not very familiar with that. It looks like a sum. So yeah.
Yeah. Still a unit. Yes. Still
Okay.
unit.
Okay.
Yeah,
Good.
okay.
Okay. Thank you. Other questions? Okay, there doesn't seem to be a question here, and we are, we already spent more than an hour. So